Okay, come. Let's start. All right. So last lesson we went through a few things. I'm gonna review those things first. Okay. Then we will move on to the next part for today's lesson. Okay. By today we can finish the chapter, and next lesson we're gonna do one final lesson for tutorial. Okay. So let's review whatever we did last lesson first. This topic is on benzene. This is benzene, right? Okay. Can we just recall the property of benzene itself, the structure? Why is benzene such a special structure? Okay, remember each carbon atom, let's start from the top. Each carbon atom is what hybridized. Okay, good. Each carbon atom sp2 hybridized. If you are sp2 hybridized, what else do you have? Each carbon has a, what other orbital does it have? Is it just sp2 hybridized orbital? You also have a p orbital. More importantly, I'm interested in this p orbital here. Because if every single carbon has a p orbital, they can all what? So imagine 6 carbons, all of them have a p orbital arranged in a hexagonal shape, something like this. What will happen? What would they all do? Would they just be standing there doing nothing? No, right? Okay, what would they do? They're all side by side, so they will overlap with one another continuously, right? Okay, so we talked about how if all of them have p orbitals, there's this thing called a continuous overlap of p orbitals. All 6 p orbitals are connected to one another. And because of that, guys, this allows what to happen if all 6 p orbitals are connected. The pi electrons in the ring can travel across the entire 6 carbons, right? So that's why this creates a delocalized pi electron cloud. This forwards over here very special. It is benzene all its special properties. But you can think of it this way, all 6 p orbitals are connected, so the pi electrons can just move freely across all 6 carbons. Okay, okay, and because of this very special property over here, this delocalized pi electron cloud makes benzene very what? Stable. Okay, good. Okay, it makes benzene a very stable structure. Okay, so we talked about a few other properties as well. Okay, some of these properties that come from the delocalized pi electron cloud. Number one, right? Okay, there's this thing called partial double bond character. So the bond length in benzene is in between that of a double bond and a single bond. Okay, if you just look at the normal double bond and the normal single bond, okay, they have their own lengths. Okay, let's just say this 0.12, this 0.154. If you take the benzene's carbon-carbon bonds, where will it be then? Is it smaller than this, larger than this, or in between? Okay, it will be in between. Okay, so we talk about how the carbon-carbon bonds in benzene will be in between that of a normal single and a normal double bond. Okay, and it's all because of the delocalized pi electron cloud. And so far, okay. At the same time, we also talk about how, can you all tell me, is benzene a planar or a non-planar bond? Okay, it is planar. Why? How do we justify that? Okay, all carbon atoms are first sp2 hybridized. What shape is that? Trigonal planar. Okay, so if all are the same, that's why the whole molecule is planar. Okay, and the last one that we talked about is this. Okay, we had a debate on whether it undergoes substitution or addition reactions, right? Benzene undergoes which one? Substitution or addition? Okay, so wait, what was the main reaction that we learned in benzene, this topic? Okay, we learned electrophilic sub, which we will recap very shortly. Okay, so benzene undergoes substitution and not addition. But why is that so, guys? Benzene has double bonds, right? Okay, benzene has double bonds, shouldn't it undergo addition? Why does it not undergo addition? What was the main reasoning behind it? Okay, it's very stable. Yes, okay, benzene is very stable. What happens when you undergo addition? You will break the double bonds. In other words, you will disrupt the stability of benzene. You can remember all that, right? Okay, if you disrupt the stability, that's bad. Okay, it's energetically what? What's the keyword that we use? It's unfavorable, not favorable. Good. Okay, so you undergo substitution instead, because instead of disrupting the stability, what do you do instead? You preserve the stability. Good. Okay, so it all boils down to the same idea. It's about preserving stability versus disrupting the stability. Okay, which one's definitely more favorable. Okay, so this is just a summary of what we did last lesson. We also went over electrophilic substitution, right? Okay, mechanism-wise, I'm not going to go through the mechanism again. We did it last lesson already. Okay, but let's recall the 3 different types of reagents. Okay, the first one will be nitration. Nitration is subbing what? Can you remember what group we are substituting? What was the electrophile? How does it look like? NO2 plus. Good. Whatever you want to substitute, okay, just put a plus and back lah. Okay, so that is the electrophile. Okay, we also underwent this thing called halogenation, which is when what was the electrophile here? Okay, it can be Cl plus, Br plus, in general, it's just your X plus, right? Okay, now the last one was slightly more tricky. Okay, this is called alkylation, and I'm sure, right, you guys can look at the name and just tell me what it looks like, right? Alkylation means to substitute an alkyl group. Alkyl groups are just made up of carbons and hydrogens, right? Okay, so what's the electrophile here? Okay, this one we go over it one more time because last lesson you guys struggled with this a little bit. Okay, if I want to make this, if I want to substitute this alkyl group into benzene, what is the electrophile here? CH3 plus. Can see the pattern? Okay, whatever that I want to substitute is just a plus at the back. Let's just say I have this now. Instead of one carbon, I have two carbons that I want to substitute onto benzene. How does the electrophile look like? Okay, two carbons, just to make sure of that. And where do you put the plus charge? Just whichever one doesn't really matter here. Okay, can see what we're trying to do here. Okay, then here they can attack the plus charge carbon. Okay, then we went through a few other slightly more challenging scenarios. Okay, I show you guys this particular scenario here. If you wanted to sub this alkyl group onto benzene, what is the electrophile like? I remember also using numbers to show you guys. Okay, so what is the electrophile here? In fact, you just tell me okay, you have three carbons, okay, so obviously you're supposed to have three carbons like that, right? Okay, where do you put the plus charge? Okay, on the second carbon, because the second carbon is directly bonded to benzene. So I told you guys to circle it out also. So that right there is the electrophile. All clear so far? Okay, so it's whatever alkyl group, you can have 1000 alkyl groups substituted onto it, it doesn't matter. Okay, you just need to know where the plus charge originated from. All good so far. Okay, now? Okay, so that's whatever we went through last lesson. Now we're gonna proceed over, continue from page 18. Okay, so we're gonna use this okay, and then build off that idea. Okay, so turn over to page 18 first. Okay. So guys, the number one thing, right, that we went over last lesson is benzene. We talked about a very vanilla, very boring benzene ring, and then we substituted things that we talked about just now. But now, today, we're going to modify benzene a little bit. So that's why this segment here is called substituted benzene. This segment here, a little bit heavy, okay, but just follow this up, okay? In other words, guys, we can have different types of substituents of benzene. Instead of just a boring ass benzene here, I can have Cl on it. And this Cl, I can tell you guys, will affect the reactivity of benzene. So this is the number one thing that I'm going to go over. All these substituents of benzene, all these additional, like you can call this like add-ons, right? Okay, you can. All these add-ons will affect how benzene reacts. I will cover this in a bit. Okay, there's also another thing that it will affect. It will affect this thing called the directing effect. Some just ignore first, later I'll come over this. Okay, but more importantly, for reactivity, guys, I want you all to bracket at the side and right there. It's all about rich versus poor. Okay, we know that in organic chemistry, we are going to attack from rich to poor. That's like the rule that you can never change. But sometimes, with all these additional weird stuff, okay, I can even have my alkyl group CH3 bonded onto it. This alkyl group can have effects on the benzene. It can make benzene. Okay, guys, benzene is it rich or is it poor? Just to get this clear first. Is benzene a rich species or poor species? It attacks electrophiles. So is it rich or poor? Okay, it's rich lah. Okay, electrophiles are poor, so benzene is rich. So guys, because benzene is rich, you can either make him more rich or you can make him less rich. Okay, all these guys can have different effects. So we're going to look into the specific categories. Okay, so if you look at page 18, okay, nothing really much there. Okay, but you see, we're going to touch on reactivity first. And guys, you will see another term. Under reactivity, right, you can see there are two separate effects. The first one is called inductive effect. Okay, the second one, which I'll talk about later, is called your resonance effect. Now, these words here seem very cheap, right? Okay, so what I want you guys to do, let's come up with a short definition. Inductive effect, we're going to discuss electronegativity difference. For resonance, guys, you see the word resonance, what do you think of? Okay, so think of this delocalization. Okay, when you see the word resonance, we're going to discuss delocalization later. We'll come to that. Okay. Now, guys, let me give you an analogy here. Okay, as I mentioned, last lesson we went through benzene, normal benzene, very plain. So you all imagine this, you eat prata, right? Okay, prata very plain. Who the hell eats plain prata? That shit is disgusting, right? Okay, so no plain prata. Today we're gonna talk about what? That's weird. Why would you eat plain prata?
It's nice.
You're supposed to add stuff to it. Okay, I'll get to that lah. Okay, as in don't eat plain prata alone without anything. Okay, so that was the previous lesson. Very boring. Okay, we just have plain prata. You don't add any shit. But today, we're gonna have two different effects. You can either make prata with curry or the criminal one will be sugar lah, right? Okay, so of course we're gonna take a look at two effects. Okay, I want you all to treat it this way. Okay, some people like to eat curry with sugar. What the hell? Okay, so anyways, inductive effect, treat it that way. Okay, for some people, y'all will like curry with, y'all will like prata with sugar. But for people like me, I absolutely hate it, right? Okay, so it depends. Okay, so I want you to look at inductive effect first. Okay, I already told you about this. Can you look at page 19? There are four types of groups, four types of people here. Okay, there are four types of people here. Okay, now I know it's printed over there already. Okay, but look at the board. The first group are your alkyl groups. Okay, alkyl groups. Guys, alkyl groups are electron what? We learned this. Electron donating. Okay, so today we're going to take a look at electron donating. And guys, what's the opposite of donating? Let me just write here. Electron donating, that means you give electrons. On the other hand, there are other people who instead of donating electrons, what do? You take electrons, right? The word over here is withdrawing. Okay, so take a look. There are two effects here. There are two terms. Some groups will donate electrons, and one of that is alkyl groups. Okay, so the first one, via electronegativity difference, alkyl groups are electron donating. Now, why is that the case? Okay, so let me show you a simple reason. Okay, I know in the notes they put there a dash, okay, but I think it's good to go through. So, okay, so you imagine this. There's a benzene here, and then there's an alkyl group. I just draw CH3 here. Okay, why is CH3 giving electrons to benzene? Let's look at electronegativity. Carbon and carbon. Are there any electronegativity differences? No, right? Okay, so let's look at C and H. Guys, CH bond, is it polar or non-polar? What did we learn? Okay, we learned that CH bond is non-polar, right? It's because the difference in electronegativity is very small. Actually have difference lah. Okay, but let's take a look at the difference. Carbon is actually more electronegative than hydrogen. So can you see the dipole moment is pointing to the left or to the right? To the left, right? Okay, so can you see this arrow here? The electrons are going towards the benzene, right? So this is an act of donating or withdrawing. Okay, so you are benzene, so you are getting donated electrons, right? So yes, okay, that's the reason why alkyl groups are electron donating. Let's look at more examples. Can you look at the second group of substituents, OH and NH2? Are these guys donating or withdrawing? Okay, you can see from the notes right here, but let's just draw our diagram. Okay, I'm going to draw this bonded to OH. Guys, C and O, who is more electronegative? O. So O is more electronegative than C. The dipole moment is pointing towards what? Okay, O. So guys, from the perspective of benzene, is this donating or withdrawing? Okay, you take this dude is stealing electrons away from benzene, right? So in other words, this is considered an electron withdrawing group. Can see this so far? And before we move on, we are going to take a look at how a benzene is getting affected when there's a donating versus a withdrawing. So imagine this, guys. What did I mention just now? Reactivity is about rich versus poor. Is benzene rich or poor, fundamentally speaking? Okay, it is rich. Okay, so I'm not going to use the word poor here. It is out. Okay, I'm going to use the word rich. You can't describe benzene as poor. Okay, benzene is rich, but now I have an electron donating group. Is he more rich or less rich? He has become more rich. And guys, if you're more rich, do you think you're more reactive or less reactive? Okay, even more rich with electrons, right? You're going to react even faster. Make sense? On the other hand, guys, look at this. Is benzene more rich or less rich? Less rich. Now, does less rich mean more poor? Now, in English, it's the same thing, right? But in chemistry, we can't do this because is benzene fundamentally poor? No, so you cannot even use the word poor in this scenario. Can you see that? Okay, in other words, guys, if benzene is not as rich as before, do you think the reaction is going to be faster or slower? Slower, no? Yeah, that's pretty much it. It's very intuitive. Can you see that? Okay, so yeah, in other words, inductive effect is like for people who eat prata with sugar. For some people, like this group of people here, sugar makes prata taste nice, more rich the flavor. But then for some people like me, okay, I just really don't like it. It just makes prata taste worse. Okay, so there are two different effects. Sugar lah, donating / spoil. Can see that so far? Can okay, same idea over here for benzene. All these guys, all these things here are like condiments to help to modify benzene. Okay, now we just continue with the other two groups. Okay, I'm sure you all can see the third group over here are all made up of halogens, right? Okay, halogens, very simple. Okay, you all take a look at the benzene bonded to any halogen. Who is more electronegative, the halogen or other? Okay, halogen, right? Again, halogen is more electronegative. So the dipole moment, same thing, pointing away or towards benzene. Clearly, it's away from benzene, right? So, guys, what effect is this? Okay, electron withdrawing. Very simple, right? Okay. Now, last but not least, we have a group made up of a lot of nonsense. Okay, so we'll get to that. Okay, so these are all like miscellaneous groups. Let me just pick out a few. Let's pick out these. Okay, and I'm going to draw both. Okay, this is how CHO looks like. This is how NO2 looks like. I'm going to draw the entire thing. Okay, and now let's consider the electronegativity difference once again. Carbon and carbon, is there any difference here? No. Okay, so if you don't see any difference here, don't just give up. Okay, let's look at beside it. So C and O, who is more electronegative? Okay, O. So can you all see, right? It is still another act of like going away from benzene. The arrow is pointing away from benzene, right? Because oxygen is very electronegative. So it's pulling electrons away from benzene. Does that make sense? Okay. Now, same thing, there's NO2. Okay, and thankfully, right, NO2 is already going away from benzene because N is already more electronegative than C. But at the same time, there's also NO bonds, right? It's more electronegative. Okay, O. So O is more electronegative than N. It will still nevertheless, right, okay, pull electrons away from benzene. Okay, there I only draw two examples, but the rest of the examples in this same group here, same thing. Okay, all going away from benzene. So you will see electron withdrawal. Okay. Okay, I'll look at the big picture. The big picture is this. Out of all these four groups, only one of them is electron donating, which is your special alkyl group. Okay, the rest all withdrawing. Any questions? Yes. You can also. Okay, so this is plus, this is minus. Okay, you can also have a withdrawing effect here. But it's also made worse because there are even more polar bonds afterwards. Just to show you, like, either way, right, it works. Okay, can move on. Okay, so we have gone through one half of the story. Okay, people who eat prata with sugar, but now let's modify it with curry. Okay, so there's another effect here. Okay, so it's just another way of enjoying prata, right? Okay, it's the same thing for benzene. I'm going to stick to the same four groups of people. Some people here, like this guy, and this is the only group of people who enjoy prata with sugar. The rest are absolutely hate it. Okay, so we take a look at curry now. Now we have to look at delocalization, a little bit more tricky. Okay, so can you all take a look at page 20? There are a few things that I need to establish first. Okay, so let me write down the word delocalization once more. And I need you all to acknowledge one very important thing. Guys, for delocalization to occur, what must happen first? Then the electrons can move freely. Just now I briefly recap on that. Before electrons can just fly freely around a compound, something must happen first. Must overlap. Yes, good. Okay, so guys, take note of this. Delocalization, go and write this down, requires overlapping p orbitals, not hybridized orbitals, none of that nonsense. Just p orbitals. So guys, we must check for this first, then electrons can delocalize. So we're going to look at the same 4 groups. I'm just going to copy that down also. Okay, can? Another thing we're going to look out for is this. Okay, let's write it here. Another thing I need you all to look out for is this. The atom that is directly bonded to benzene. This is what we're going to focus on. Just the atom directly bonded to benzene, whether it has lone pair of electrons. We're going to check for this. Okay, always look at this atom and check if it has a lone pair. So we're going to establish this first. The first one we're going to draw is your alkyl group. Look at the atom, the carbon atom directly bonded to benzene. Does it have lone pair? In fact, let's ask another question. This carbon here, then what hybridization is it? This is a sp3 carbon. Good. If this is a sp3 carbon, does it have a p orbital? No. If you have no p orbital, is there going to be delocalization? No. So in other words, guys, that's why there's a big fat nail over there. Alkyl groups, mostly carbons. Carbons don't even have lone pairs. You all will probably not see carbons with lone pairs. It exists, okay, but very rarely you all will see. If there's no carbon with lone pair, there's not going to be any delocalization at all. Okay, so just nail down. Quite simple, right? Okay, we're just going to move on straight to the second group. Okay, this second group is important. Okay, can? Look at the next one. We're going to take OH and bond it onto benzene. Now, first of all, can you tell me, does the oxygen have lone pair? Have, right? Okay, there's 2, but let's look at one only. Does the oxygen have a p orbital? Okay, I know we never learned hybridization of oxygen before. Okay, but does oxygen have p orbital? Have, because 1s2, 2s2, 2p4, right? Okay, the configuration of oxygen allows for p orbitals to exist. And guys, I'm looking at an atom directly bonded because look at the carbon of benzene. What does that carbon have? P orbital. In fact, all 6 of them have p orbitals, right? I'm just going to draw for one of them. Okay, go and draw in this diagram also. What will happen to these 2 p orbitals? They will just what? Just stand there. They can overlap, right? Because they are literally right beside each other. They can overlap. And now, once there's a path connecting the O to the benzene, what will happen to that lone pair there? What will he do? Will he just stand there? Electron stationary, you just sit there. No, right? What can he do now? Yes, the electron is very active one. Oh, suddenly got path for me to move. I'm just going to fly into benzene straight. It's going to join the fun now, okay? Because we have the pi electrons moving in the ring here, but then the lone pair wants to join in that fun. Guys, look at this diagram here. Draw in this arrow inside as well. Is this an act of donating or withdrawing? Okay, you are the benzene now. Can you see the electrons are now new people coming in? New electrons are entering benzene. So that's why this is an electron donating group. In other words, you see this group of people with sugar, it makes prata taste a bit worse. But with curry, it makes prata taste better. Because you can see, guys, donating makes the ring more rich in flavor, in that sense. Can you see that? Okay, so we have 2 conflicting effects. Later we will come to the overall. Okay, for now, you all just focus one by one. Any questions? Can Okay, halogens very similar. Can you tell me, do halogens have any lone pairs? Okay, have, right? Okay, there's 3 lone pairs there. Okay, does it have a p orbital? Okay, most atoms have, right? 1s2, 2s2. Okay, so there is a p orbital holding the lone pair as well. Again, what will this p orbital do? Okay, overlap with the pi electron cloud of benzene, and then what will happen? What will happen to the lone pair? It will just delocalize into benzene. So guys, is this donating or withdrawing? It's another act of donating. Okay, I want you to find some space and then write down the explanation for whatever I just discussed. Okay, there's a bit of space there. Okay, find some, yeah, okay, just find some space. Okay, let's write this down first. Okay. This explanation for delocalization is a must. First, p orbital of, you're going to use oxygen, of oxygen overlaps with the pi electron cloud of benzene. Look at the words. I say that benzene is a pi electron cloud because that's already established. It just joins in the fun. Okay, so it overlaps with the pi electron cloud of benzene. And this allows the lone pair, so lone pair of electrons on oxygen, it then is able to delocalize into benzene. Okay, so let's stick with these 2 points first. This delocalization are the different effects we can talk about. Okay, but we stick to this first. Okay. Any questions here? Cannot? Okay, we have 4 types of people, 4 groups of people. We're going to look at the last one now. Okay, basically all the random ones now. Okay, let's throw in there. Okay, this is a little bit weird. Okay, so just follow me on this. So far, all good? Can we take a look at the atom directly bonded to the benzene? Does it have a lone pair? Look at the first one. The CHO. Does it have a lone pair? Don't have? Okay, carbon no lone pair, I already mentioned just now. You can already see 4 bonds there. So guys, if there's no lone pair, is there going to be any of this delocalization into benzene? No luck. So if it's, can it be donating? No. It is just, the opposite of donating is just withdrawing. Okay, so this one I know the definition here is a little bit loose. Because if you do not have any lone pairs, but yet that you can see a lot of polar bonds here, it will still undergo a withdrawing effect. This is slightly similar, right, to the previous one. Because the previous effect, we were looking at electronegativity effects. But yeah, okay, it still works. Same thing here, guys. This nitrogen here, does it have any lone pair? In fact, for all these groups over here in this same category, does it have a lone pair? No. And you can tell that there's no lone pair because nitrogen here, you can see, it already forms a native bond. So the lone pair become bond pair already. So there's no more delocalization, and yet there's so many polar bonds pointing away from benzene. So it also falls under withdrawing. You can see that? Yeah. And those are our 2 effects we've covered for all 4 groups of substituents. Okay. Now we are going to consolidate between these 2 effects. What's the overall? Okay. And if you have your data booklet, I think it's good to take it out first. Okay, later I'll tell you all about what is, later I'll tell you all how this is tested. Okay, but you all take a look first. It is, I know it's a lot over here. Okay, there's so many substituents, there's a lot here, right? And thankfully, a lot of this, in fact, all of this can be found from the data booklet. I'll tell you how to read the data booklet later. But you don't need to memorize this. Then why am I teaching you all this? It's because you all need to know how all these donating and withdrawing effects are like. You don't want to be just referring to the data booklet all the time. Okay, you need to understand these 2 different effects. Okay, with this. Okay, so anyways, okay, with this said and done, look at page 22. Okay, on page 22, we're gonna understand, right, the overall effects, and it's actually quite simple. Okay, the table there is very nicely shown up. Inductive resonance effect. Can you see that? Can you look at the first group? Okay, alkyl groups are electron donating with the inductive effect. But then at the same time, there's no resonance effect, guys. What's the overall effect? Donating long. It's not very simple, right? Okay, you all can take a look. Can you look at the last category? The last category is withdrawing and withdrawing. So overall, what's the effect? Also withdrawing, cannot overall suddenly change to donating, right? Doesn't make any sense. So first and last, settle, finish. Okay, but let's look at the second and third one where you see a little bit of a conflict. Okay, so guys, look at the second one. Inductive is withdrawing. Resonance is donating. Guys, look at what's the overall effect. Overall effect is donating, right? So can you tell me which effect is more significant, inductive or resonance? Resonance, because guys, these people they can enjoy prata with curry and sugar, but then they just prefer one of them. There's going to be a preference. It's the same idea over here. So can you go and put the the inequality sign? Okay, the inequality sign, just go and put it that the donating effect is more than the withdrawing effect. So that's why overall is donating. Can see that? Okay, so let me just write it here. Okay, so I consolidate here. This is inductive, and this is resonance effect. Resonance effect, this is donating and donating. Okay, look at the second and third one only. And then there's the overall. Okay, so if the first one overall is donating, right? It implies that the resonance effect is more significant. Later we'll briefly explain why. Okay, guys, can you look at what's the overall effect for halogens? What's it? Okay, it is withdrawing, right? So if with this information, what does that mean? Which effect is more significant? Inductive or resonance? Inductive has to be more significant. Why is that so? We will explain in the next page. Okay, but anyways, all these overall effects can be found in the data booklet. I'll teach you how to read it later. Okay, Ken? Any questions? Okay, page 23. This here, you will rarely need to use. You rarely need to know, right, why this one's more important than this one, why is inductive more important. But I think it's good to explain this. Okay, so let's write down the answer of page 23. Okay, so the question is saying this, for OH and NH2, resonance is more significant. Now guys, take a look. Why is resonance more significant for this group? Let's draw in the diagram first. Okay, we have OH and NH2. Okay, and then on the other hand, we have halogens. Okay, let's write it here. Now guys, when we talk about resonance, okay, we talk about delocalization. And we need to look at its fundamental idea of overlapping p orbitals. Now let's look at what exactly is the p orbital used here. We established that all of them have p orbitals involved. And the p orbital is holding a lone pair, then there's overlaps at 1 knot. Can you tell me for oxygen and for nitrogen, since they are the same group, what p orbital is it exactly? Okay, so what's the configuration of oxygen? Okay, what's the configuration of oxygen? It's like 1s2, 2s2, 2p4, right, around there, right? Okay, for nitrogen, it's also 1s2, 2s2, 2p3. So that means the p orbital we're going to use here is just the 2p orbital. Okay, makes sense? Okay, for the halogen, guys, halogen, what orbital are we using? Halogen, we start off with chlorine. Okay, you see, it's only chlorine, bromine, iodine, no fluorine. Chlorine, what is the configuration? Where does it stop? 3p, right? Because that's the valence shell. So this guy here uses the 3p orbital. In both cases, it's p orbital. So at the end of the day, they will overlap, there will be delocalization. But it's actually the size of the orbital that's different here. Okay, follow me through this. Guys, what's the difference between 2p and 3p orbital? What exactly is the difference? Okay, it's further away. Okay, but more importantly, guys, the size is different. Which, again, 2p, is it bigger or smaller? Smaller. Okay, guys, let's do this. 2p orbital is smaller in size. If you have a smaller orbital, does it overlap more effectively or less effectively? Okay, good. Smaller atoms, smaller orbitals overlap more effectively. And guys, delocalization is about overlapping p orbitals. On the other hand here, 3p orbital is larger. So guys, does it overlap better or worse? Worse. Okay, I'm just contrary, it's just the opposite. It overlaps less effectively. Now guys, I say this again. Delocalization is about overlapping p orbitals. So if this one overlaps more effectively, this one overlaps less, which one has a more significant delocalization? 2p. 2p will have more effective delocalization. In other words, the delocalization is to a greater extent. Okay, just write this in point form. You don't really need to write like full words. You just follow me through this. Whereas for this one, the delocalization is to a smaller extent because it overlaps less effective. So can you all see the link now? Why is it that for this group here, the resonance is more significant? You can see that? If the delocalization is very effective, that's why it is greater than the inductive effect. Okay. Okay, because the electrons, once they overlap already, right, the electrons will just go into benzene. That is a donating direction. You can see that. Is donating into benzene. Is that what you're asking? Yeah. Electrons are being donated into benzene because there's a path for being so. P orbitals overlap already, then the lone pair on the oxygen can delocalize into benzene. That's the act of donating. You're giving, not taking. Okay, it can withdraw via the inductive effect, yes. But what we are saying is this, we are explaining in terms of the delocalization effect. We have compared, this delocalization is very, very significant. So significant that it outweighs the other effect. So that's why the overall effect listens to the resonance effect instead, which is donating. On the other hand, guys, if the delocalization here is to a smaller extent, what does that mean? Which effect is more significant? The inductive will be more significant instead. So the resonance here is not very strong. So end up, your inductive effect ends up overtaking it. Can see that? Okay, inductive effect is now the one that you listen to. So it's a battle. They have to pick their poison. They do. Is it inductive or is it resonance? If it's conflicting like these two scenarios here, they're gonna have to decide which one is more powerful. That's the overall effect. And how is explained? How is it more powerful or not? We're gonna look at the resonance. How good is their delocalization? This delocalization good, so we follow the resonance effect. This delocalization weak, so that's why the inductive effect takes over instead. Does that make sense? Okay, again, this explanation here is for your own understanding. Okay, we're not really going to use this much in anything. Okay, can? Okay, so we'll slowly get to what we have tested. Okay, but anyways, that's page 23. Oh, okay, that. Okay, I assume you guys probably don't have your data booklet at your disposal. So can you all take a look at page 25 first? Okay, I cut out the segment from the data booklet that is needed. So now before we move on to the next segment, I'm going to teach you guys how to read the data booklet for this portion. Okay, can? Okay, so flip over to page 25 first. Okay, 24 will come back after this. See that cutout there? See that screenshot? Okay, see this table. This table contains the 4 groups. Okay, why are there only 3? You'll see 3 groups only, right? It's because now look at the leftmost one. Alkyl is combined with the rest of the dunes over there. Okay, so alkyl group is part of it. Okay, and you see, they don't use the word electron donating, they use the word activating. So can you all write this down? Whenever you see the word activating, right, it means electron donating. On the other hand, when you see deactivating, it means electron withdrawing. Okay, remember this, guys. When there's electron donating, the benzene becomes more rich or less rich. More rich, right? You donate, so the benzene becomes richer. Okay, you withdraw, that means the benzene becomes what? Less rich. So in other words, guys, more rich is better, right? You react faster. That's why more rich is used the word activating. If you deactivate the benzene, it's to make benzene not as powerful as before. Okay, I say again, you activate benzene, benzene becomes more powerful in a sense. If you deactivate benzene, is to make it less powerful. Okay, so those are the words there. Can see that? Okay, and all these are the overall effects. Again, that's why you can just refer to the data booklet. But you need to know where all these effects come from. That's why we went through slowly. Can so far? The final row at the bottom, we'll come back to that. So can you turn over back to page 24? This is an example of what we're going to be tested using this information here. Okay, so can you just look at the question first? Okay, and then just take a look at the 2 structures. Okay, can? Now look at the question first. Okay, let's not look at the structures here. Explain whether phenol or thymol or undergoes electrosuck more readily. A few things. Now, first of all, highlight the word electrosuck. When we look at electrosuck, what part of the molecule is reacting? What part of the molecule? There's so many different shit here, right? Okay, what part of the molecule is reacting? What undergoes electrosuck? The H. Okay, basically the H on the what? On the benzene lah. Okay, so electrosuck means we have to look at benzene getting affected in this entire process. Not the OH, not these groups here, just benzene. Hey guys, the next word is more readily. More readily here, what are we discussing? We're discussing how fast or slow benzene reacts, right? So this goes to our idea of the reactivity. This is a reactivity factor. Okay? And as we mentioned just now, reactivity is all about rich versus poor. Let's identify first. We don't want to use the wrong keyword. We are talking about benzene here. Is benzene rich or poor fundamentally? Rich. So get rid of the word poor first. We're not going to use it in our vocabulary. Okay, it's just rich for this question. So it's about whether benzene has become more rich as a result of whatever those weird stuff on it, the substituents, or has benzene become less rich? Can see that? Okay, right. Okay, your answers only split into 3 points, and then you're pretty much settled. Guys, let's again, the first point is to place spot the difference. Okay, you just tell me what's the difference between phenol and thymol? What does one of them have that the other guy doesn't have? Alkyl groups. Do we compare OH? Do we talk about OH at all? No, both of them have. Okay, so the fact is thymol has alkyl groups that phenol doesn't have. And alkyl groups, can we just say, oh, alkyl group? How do you describe alkyl groups? What effect does it have? Yeah. Exactly. Okay, so first of all, let's tell me this. Thymol has electron donating alkyl groups, while phenol doesn't. Okay, so the first point, very simple. Place spot the difference. Now, can you just tell me, so what? If thymol has electron donating alkyl groups, does benzene become more rich or less rich? More rich. Tell me that. Okay, so thymol, okay, or you tell me the benzene ring in thymol. Okay, is now more electron rich. Now I have to write down an alternative way of answering this. Okay, you can either say more electron rich or it increases electron density in the benzene ring. Both are explanations you will see that. Okay, choose which one you prefer. Okay, personally, I would prefer this, more electron rich. But if let's say you never identify your rich or poor correctly at the start, then the word electron density is very safe. Okay, very neutral. You just tell me whether increase electron density or reduce electron density. That one's a lot more safe as well. Okay? And guys, the final point, okay, we answer the question. So does it react more quickly or slower? Okay, it's more rich, right? So definitely it's going to be faster. The more rich something is, it's definitely going to attack faster. Okay, so the third point, unfortunately, we can't just write, oh, it reacts faster. Okay, there's a phrase that we need to follow. Okay, so that means thymol is more susceptible, okay, to electrophilic attack. Okay, and this just means it's more reactive. Okay, highlight this entire phrase here. Okay, again, all these explanation questions I need you to highlight the keywords. Okay, it's just more susceptible. Okay, you just need to use this phrase here. Okay, why electrophilic attack? It's because the benzene attacks what? Benzene is rich, it must attack something that is poor. And the poor guys here are your electrophiles, right? Okay, so it must be electrophilic attack. In future, we will see nucleophilic attack as well. Okay, again, that was a different scenario. We won't touch on that yet. Okay? Any questions here? Good? Yeah. Okay, so this is usually what you test. Okay, you're supposed to compare the reactivity of two different compounds. We'll try more of this. Any questions? Okay, if that's okay, with that said, we have completed the reactivity segment. These random substituents here can make benzene richer, or less rich, or poorer, or less poor, whatever. But there's also another effect. All these random substituents that you put on the benzene, it can affect this thing called the directing effect. Okay, so let's move on to that now. Okay, this one is only one page, so you can imagine it's not very difficult. Okay, and this one, right, I need you all to refer to the cutout from the data booklet that I showed you guys just now. Okay, or you can just refer back to page 25, lor. Okay, oh yeah, it's right there, it's right there. Okay, so anyways, directing effect, what is going on? Now, first of all, guys, what if if you have a normal benzene, and I want to substitute, let's say, a halogen Cl+. Does it matter where the Cl+ is getting substituted onto? Does it matter which H is getting substituted onto? Doesn't matter, right? Okay, it's the same O, same O. So you're just gonna substitute on any H, it doesn't matter. You put here, it's all the same. Okay? But what if okay, the benzene currently, right, already has something else? Let's just say the benzene already has alkyl group, and you want to substitute Cl onto this particular compound. First of all, what do you substitute? Do you substitute the CH3? Have we learned such a reaction where electrosub substitutes the CH3? Electrosub is to substitute what? Electrosub substitutes the H only. Okay, so take note of this, sub H only. You can't, whatever that's substituted on the benzene now, you restart that forever, you can't change. Okay. Now the issue is, does it matter where the Cl is being substituted onto? You have to put Cl here versus here versus here. Is it different? It's different, right? Now, so there will be rules as to where this guy is supposed to go. First thing that you all need to know, this is position 1. The OG basically is the guy who's already staying on the benzene. Now, if a new guy decides to come in and stay with CH3, he obviously has to listen to CH3's instructions, right? So what does CH3 tell him? He tells him, you can only go to the 2nd or the 4th position. Because, can you all look at the data booklet, the last row. It says that 2n or 4. This means 2, 4 directing. You see, alkyl group, the first column, okay, is 2, 4 directing. Meaning to say, guys, the Cl, is telling the Cl you can only go to the 2nd or the 4th position. Meaning relative to CH3, you can either go on the 2nd or on the 4th position. Can you go on the 3rd position? Okay, it's not that it's not possible. It is possible also, but the chances of doing so are much, much lower. Okay, so I want to take note. Okay, chemistry is not foolproof one. Okay, you will get a 3rd position also, but the chances of it is much lower. Okay, 2 and 4 is much higher. So guys, let's try over here. This is very example driven. I want you to write down as many examples as possible. Okay, so you can either go here or you will go here. Okay, 2 possibilities. Okay, I'll give more examples. Okay, guys, why is it that this guy tell him to go on the 2nd or the 4th? Why does he not tell him to go to the 3rd position? You don't need to know that. It's not syllabus. Okay, thankfully you just need to follow. This is a puzzle game. It's just where they will slot the guy only. Okay, this is only 1 page. Okay, so this one don't treat it too seriously. It's just like, oh, put on the 2nd, put on the 4th. That's it. Yeah, okay. So let's do a bit more practice here because don't have much questions here yet. Okay, guys, let's look at the 2nd scenario. Now the issue is when you start doing this, a lot of students do not know whose instructions to follow. Guys, do you follow the new guy's instructions or the good old guy's instructions? Who do you listen to? Do you listen to the senior or the junior? right? You listen to the seniors, right? Okay, the senior is the person who's already staying on benzene. He knows his shit. Okay, so guys, we have to follow this guy's instructions. Can you just look at the data booklet and just tell me what's his instruction? Okay, good. So this guy in particular, tree directing. Simple, right? Okay, so guys, where should this be directed onto? Okay, third position. Take note, first position is the guy, the original guy. Okay, and then the third position is there. Okay, so just go and draw that. So these two scenarios, simple, right? Okay. I'm going to slowly introduce more scenarios. Okay, so I'm going to take a look. Yeah, okay, let's take a look at this. Now, there's already two people living on benzene. The third guy wants to come in. Okay. Okay, I'll just help me go and find out what are the directing effects. Okay, look at this guy. OH, what's his instruction? Okay, go and practice looking through, getting familiar with the table. What's OH's instruction? Okay, he tells NO2, bro, you can only go on the second or fourth position. Okay, but how about CO2H? Okay, then this guy come in and say, no, don't go on the second or fourth. You can only go on the third position. So who does he listen to? Okay, so first of all, I need to imagine this first. 2 or 4 directing is with respect to this position 1, OH, can see that? So that means NO2 can either go on the second or the fourth position, can see. I draw arrows first. Now, this is CO2H. 3 directing, is it with respect to CO2H or with respect to OH? CO2H, because it's instruction, right? So now this position 1, so where is the third position? 1, 2, 3. Can you substitute here? No, it's occupied already. So you go the other way. 1, 2, 3. Can you substitute here? Okay, can. There's a space. Can you see this? This guy tell NO2 to come here. But this guy tell NO2 to come either here or here. 3 different positions, right? What is the most likely product? What is the major product? Who do you think you're going to listen to? Okay. OH is what effect? Okay, I'll just look at the data booklet. Activating. CO2H is what? Good. And guys, at this point, it's all about listening to the person who has more experience, the better person. So whenever there's any conflicting positions, always listen to the activating substituent. So the rule is this. The more activating substituent, okay, directing effect must follow him. Okay, follow the more activating substituents effect. Okay. Now there are plenty of scenarios, but I don't want to touch on the ones that go even further. Never mind, we don't touch on that yet. Okay, we understand the base first. All these very simple, but then this one starts getting a bit tricky when you're conflicting positions. Okay, there are other scenarios such as this. You have one activating, one deactivating, right? And depending on its position, they might end up pointing to the same position. Then the one, right, okay, they reinforce each other. Then that one is okay. But if they compete with each other, as you can see, you must follow the more activating substituent. You can see that? Okay, it's a competition. Right? Okay, so we'll practice more of this in the tutorial. Okay, for now, you can understand this concept quite simple. Okay, you give instructions to someone who's new, who's coming in. Okay, that's pretty much it. Any questions? Okay, please ask now. Okay, yeah. You can both deactivating, and you can both activating. Okay, if both are deactivating, right, that one you probably won't give because you're gonna have many different products. Okay, but I think we go through this. Okay, can you look at this last scenario here? What if we have okay, guys, look at this one. This scenario a little bit tricky, but I think it's good to go through this now. Okay, so just now we talked about how, okay, what's activating, what's deactivating. You follow these two things. Okay, simple. Okay, guys. OH, what's its directing effect? Okay, it is 2,4 directing. CH3, what's its directing effect? Also 2,4 directing. Now OH is what effect does it have on the benzene? Okay, CH3 there. So what's going on over here? Both of them are activating. Who on earth do I listen to? And they are both 2,4. Okay, but they are 2,4 it's with respect to different positions. Can see that? 2,4 is 2, 3, 4. Is that, can you substitute on 4? No, or you can go the other way. 2, 3. Okay, it's the same thing like the substitution. 2, 3, 4. 4 is still occupied. But 2, 4 with respect to this guy is where? 1, 2. Or 1, 2. Can see? So it's different. They are not reinforcing each other. Can see that? So who on earth do I listen to? Do I listen to OH or CH3? Guys, they are both activating, correct? But what the data booklet has not told you, that's why you went through all of that shit just now, right? Is this. OH, in what way is it activating? How does it donate electrons to benzene? Can you remember? How exactly? Okay, remember, OH, what's the overall effect? The fact that it's a lone pair, what will the lone pair do? Okay, the overall effect is that it's donating. So we don't talk about the electronegativity difference. Okay, the lone pair here delocalize into benzene. In other words, this one, right, is donating via the, what's the effect called? Resonance effect. Now, CH3 is also electron donating, but what effect is this? It's done via the inductive effect. And I can tell you all this right now. Whenever you see this scenario, right, the resonance effect is definitely more powerful than the inductive effect. Delocalization always wins, it's more powerful. Okay, now this is not the same as just now. Yeah, I know just now we talked about how OH has two effects, both resonance and inductive. But resonance is more powerful. Now this one is resonance versus inductive across two different substituents. So here, resonance is stronger, so that means we must follow OH's directing effect instead. In other words, the major product will be on the second position with respect to OH.
So this case is always the resonance.
Yes, resonance, you listen to resonance more. Resonance is even more activating than this inductive effect. That's why I say this one, I was contemplating whether to show you guys this now. Okay, sure now. This is your ask. Okay, if not, we'll usually go through this whenever the question comes. Okay, so this is right here. This is not the only product. I want you to know. It's the major product, but of course, you're gonna have variety of products here. Okay, yes. Okay, but once we're done with this, we have to move on to page 26. Okay, it's going to be quite intense today's lesson. Okay, we have to continue with the stuff. Okay, and I can go on and on with the different possibilities. Okay, that's why we need to look at questions eventually. Okay. Let's say you say you wanted to have lesson on Monday to Wednesday, one of those days, right? Or
at night.
probably at night. Or why at night? Yeah, because I thought holidays now we can just do it early in the day, then don't be so tired. Yeah. All 3 days cannot, is it?
Yeah.
Yeah, let me just do one final time and I will finish. Okay, anyways, let's continue. Okay, don't die yet, later I'll give you a break. Okay. Oh no, why so sleepy? You guys, the holidays supposed to be energized. Oh, you watch your World Cup? Oh, you watch that? That's good. Dedication. I thought you woke up watch World Cup. This is what I expected. Oh, I watched lecture. Okay, good. Very nice. That's bad. Yeah, tell you what, we just take a break now since you freaking go toilet. Yeah, okay, just take a break first, take a break first. Okay, come, we finish up the notes. Okay, once done, we can do some stuff. Okay, so page 26. Okay, we're gonna continue with methyl benzene. Okay. Earlier on, right, we discussed just benzene and its reactions. Now we're gonna look at methyl benzene and its reactions. Okay, do you all realize, right? Now we have two parts to this molecule. We have both the benzene and an alkyl group, or specifically just a one carbon methyl group. Okay, can we just specify what are the possible reactions on the benzene ring? Or on this methyl benzene to be more specific. If it has a benzene ring with H's, that means it can undergo what reaction? Electrosub. Okay, good. On the other hand, I also have this alkyl group here. What possible reactions can an alkyl group undergo? Any idea? Alkanes. What can alkanes undergo? In fact, what's the only reaction that alkanes can undergo? FRS, exactly. So you can see I have two separate parts to this molecule. Each unique part of the molecule has their own reaction. Okay, but that's not all. Okay, later on we'll see that there are other possible reactions also. But to be very sure here, right, this CH3 over here is known as a side chain. Okay, anything that's attached on benzene doesn't have to be CH3, can be anything. Anything attached is called a side chain. Later we're going to look at other possible reactions also. But let's look at electrosub first. Now, when it comes to electrosub, it is the same as before. Okay, we have the three possible electrophiles. Can you all remember what are the three electrophiles that we have learned? Okay, we have NO2 plus, right? Anything else? Just throw out some ideas. Okay, we have the halogens like HCl. Okay, what's the final one? We have some entire alkyl groups, right? Okay, your alkylation. So anything like you did legit anything with a plus over there, any R group with a plus. Can? Okay, so same thing, all these three guys have the same effect, but can you all look at page 26? Okay, do you all realize, right? Okay, I'm gonna go over nitration first, and this will set the tone for the rest. If I have CH3 over here, and I want to substitute an NO2 plus onto it, okay, can you all see how many products can I possibly get? Okay, based on what's in the notes. Okay, you can get two possible products because CH3 is what effect again? What's its directing effect? Okay, it's activating, good. Okay, but where does it point the NO2 plus towards? Okay, good. Because it's the 2,4 directing effect, right? So that's why you can get two possible products. So that's number one. Okay, because CH3 is 2,4 directing. Just check it out. Alkyl. Yeah, okay. So we have substituted over here, or we can substitute down here also. So we have accounted for the directing effect. But at the same time, guys, remember CH3 also can affect the reactivity of benzene. What else do you all mention also? CH3 has what effect on the reactivity? Is electron donating or is it electron withdrawing? Okay, it's electron donating, right? Now, if you can donate electrons to benzene, benzene has become more rich. Now, if you are more electron rich, are you more reactive or less reactive? You're more reactive. Okay. And can you all look at the reagents and conditions? Okay, and then there's going to be something a little bit special. For benzene, a normal vanilla benzene, this one requires concentrated HNO3, concentrated H2SO4 catalyst, and they said 55 degrees Celsius or warm. Okay, this was what we went over the last lesson. But for this question here, let's make a guess. If this methyl benzene is more reactive than a normal benzene, do you think your conditions are stronger or milder? It's more reactive. Do your conditions have to be stronger to push it to react, or can it be milder? Because it can react by itself. It's milder, right? Because it's very reactive already. So your conditions a little bit enough already. They don't need to be so strong. So milder conditions will suffice. So in other words, guys, can you all take a look at your answer here? The conditions required, you also need HNO3 concentrated, same thing. You also still need a catalyst, H2SO4. But finally, guys, can you all take a guess what the temperature is? Higher or lower than 55? Okay, lower because milder conditions, right? You don't need to make it so hot. So that's why you can either use 30 degrees Celsius but if you don't want to memorize numbers, it's the word room temperature. So you can go and highlight the condition, the temperature used. Okay, this is the important part. So depending on what substituent it is, okay, depending on what substituent it is, okay, I need you all to put the appropriate temperature. Okay, and this is explained in the next page as well. Okay. Turn over to page 27, under halogenation, highlight the room temperature also. You can see previously it's warm, but now room temperature enough already. Okay? And the next thing is, look at the question over here. Let's answer, why is it that it requires a lower temperature? Can we look at the three-step explanation once again? First of all, what does methyl benzene have that benzene doesn't have? What's this thing? Okay, how do we describe it? Yeah, okay. Methyl benzene has. How do you describe the whole thing? Good. Okay, it has an electron donating alkyl group. And what does this mean? Yeah. Okay, this makes the benzene ring more electron rich. Finally, then, what's the final point that we mentioned? Okay, how do we say that it is more reactive? So, right. Okay, yeah, how is it more reactive? Yeah, it's like bringing the Lord is like looking onto me now. Okay, but anyways, okay, the methyl benzene is more what? So it's S. Yes. But okay, methyl benzene is more sad. Okay, more susceptible to what attack? Yes, okay, more susceptible to electrophilic attack. In other words, it's just more reactive now. But guys, we need to link back to why it has a lower temperature. Because it is more reactive, that's why the conditions are milder. Okay, yes. So just add that in. It does milder conditions will suffice. Done. Okay, again, it's good to highlight all the keywords. Electron donating group, more electron rich, more susceptible, and hence milder conditions. Okay, 3 steps. Right, we'll go with this. You can also take a look at the last question on page 27. Let's read through that first. Let's make a guess what could possibly happen. Yeah, come to that soon. Okay, as we move on to the next question, they are asking, right, what happens if the nitration of benzene is done at a higher temperature? Now, guys, what's the temperature required? Okay, so for benzene now, what's the temperature required? Okay, benzene. So benzene, 55 is enough. But what happens if you choose to use something higher than that? Let's say 60 degrees. Or even higher than that, 60, 80 degrees. You make it very, very hot. What could possibly happen here? Any guesses? No, okay, benzene still cannot break. Okay, good guess. Okay, but benzene will not break. We are just looking at the reaction here. What will happen to the reaction? Will you get a different product, that kind of thing? Okay, first of all, what will happen to the rate of the reaction? Okay, definitely faster. Okay, but that's not really what we are concerned with. Okay, but just take a look. If you use 55 degrees, it is just nice to put one NO2 onto benzene. But if you make the conditions even stronger, what could possibly happen? You substitute one NO2 for just at 55 degrees. If you put a higher temperature, you might end up substituting more times. So you might have multiple NO2s. In other words, the answer to this is that there's a possibility of multi-substitution occurring. Okay? Possibility of multi-sub to occur. So for instance, guys, this 130 degrees enough already for methyl benzene. But if you choose to use 55 degrees, what must happen? Like what could happen? You might have benzene, or you might have NO2 substitute on which positions. Okay, instead of using 30, okay, if you use 30 degrees, this is suitable for mono sub, just one substitution. Sub on the second or the fourth position, correct? But if you use 55 degrees, what might you get? Okay, you can sub on the second and the fourth position. You might substitute on both. You can see that because your conditions are even stronger. You might push it to substitute more times. You can see that. Okay, so that's why the temperature must choose carefully. Okay, guys, let's look at page 28. We kind of went through this just now already. We have an alkyl group, so alkyl group can definitely undergo FRS. Okay, and so on. You all notice there's actually a difference here. If you undergo FRS, if you want to substitute this H, you must use FRS, UV light, all that stuff. You see that? So you turn the CH3 into something like CH2Cl. But guys, if I want to substitute this H over here on benzene, can you use the same conditions UV light? Is that enough? No, you must use all the different catalysts and whatnot. Okay, so see the H's of different functional groups have different reactions here. Okay, so take note FRS, you think of the word UV light. Okay, that's page 28. Okay, move over to page 29. You're pretty much at the last segment already. Okay, so as I went through just now, this part over here is known as a side chain. And this side chain can actually undergo oxidation. So the name of this reaction here is called side chain oxidation. We're going to take a look at how this works. It's a little bit special, the mechanics. Okay, it's kind of like oxidative cleavage like that. But here is like kind of similar. Okay, so can you all take a look at page 29? Now there are a few things there. Okay, but I suggest you just look at the board here. Okay, I have a side chain, and this side chain is just your methyl benzene, one carbon. When I undergo side chain oxidation, sometimes oxidation you will see this bracket, and you will end up with this. It will turn into CO2H. Guys, what's CO2H? Can you recognize the function? Carboxylic acid. Good. Okay, and this is a specific compound called benzoic acid. And I'm sure you all can guess why, because there's a benzene attached to a carboxylic acid. Clear enough, right? Okay, but again, let's go over the basics first. Okay, the reagents and conditions is the same as what we use for oxidative cleavage. You need an oxidizing agent, KMnO4. You need to have a medium. Remember, I told you guys, KMnO4 doesn't work without any medium. You must use either H2SO4 or NaOH, but please use H2SO4 because then you remember less observations. Finally, you need to heat up. Okay, most oxidation need to heat up. Okay. Now, next, observations. The observations here are a little bit more than what is expected. Okay, guys, what will happen to KMnO4 if the oxidation is successful? Good. Okay, so number one is purple KMnO4 will decolorize. Okay. But at the same time, guys, I want you to add this inside. Your benzoic acid is actually a white precipitate. This is something that a lot of people tend to forget. Okay, so white precipitate of benzoic acid is formed. Okay, let's highlight that, right? Now at this point, you'll be asking me, right, how on earth does this work? Okay, you just turn it into benzoic acid, yeah, okay, it feels like nothing is going on over here. Okay, now you can see at the bottom of page 29, there's a big fat box with an important note there. Okay, you read it, okay, you probably don't understand what it means. Okay, so I want you all to look at examples. There's some space below that box, so I need you all to write a bit smaller because I'll go over quite a few examples here. So guys, let's take a look at the first one. What happens if my alkyl group, my side chain, has more than one carbon? Let me show you guys this once first. No matter how long the carbon chain is, that's what the notes say also. No matter how long it is, you will always get benzoic acid. Okay? No matter how long the carbon chain is, you will always get benzoic acid. A safe one. Okay? And guys, what do you notice happened? The side chain has how many carbons here? 2, right? And then what happened? It got cut. So how this works is this. The carbon that's attached directly to benzene, I will call it as number 1. And carbon 1 is the one that becomes benzoic acid. Clear with that? Okay. But at the same time, guys, what will happen to carbon 2 then? carbon 2 has actually broken off. So I need you to draw this line to show that carbon 2 has been broken off. Guys, if you have one carbon, you try to oxidize this one carbon, what do you think you'll get here? Yes, you'll just get carbon dioxide. And probably water as well, but I'm more interested in carbon dioxide. And what I want you guys to do, go and draw this line that cuts carbon 1 from carbon 2. Number 1 and 2 also, and number the 1 and 2 over here as well. So you can see what exactly carbon 1 became, what carbon 2 became. So guys, when there's carbon dioxide, what's the observation that you see here? Carbon dioxide means got effervescence. Yes, okay. Whereas this first one only a white precipitate. So guys, if this happens, there's an additional observation here, effervescence of carbon dioxide gas. Not gonna write it down, okay, but then it's also mentioned. Okay. But this doesn't show you guys a full picture yet. So what I'm going to do now, I'm going to now draw 3 carbons, and this is when I'm going to use skeletal formula already. Okay, no more structural formula. Let's apply the same rules, apply the same technique here. Guys, what is the one product you will form? You will form benzoic acid. Okay? Guys, go and number the carbons. Okay, go and number the carbons up. Okay, number the carbons. Remember, our carbon 1 must be attached directly to benzene. So 1, 2, 3, correct? Okay, so carbon 1 is always benzoic acid. Okay, what's the second thing we need to do? How do we determine the other products? We have to cut 1 away from the rest. Now, don't cut 2 and 3 or anything. Remember the rules. Just cut 1 away from the rest. So can you see 2 and 3 are still together? Now, what's going to happen here is actually this. The next product you're going to get is also going to be a carboxylic acid. Now, I'll come back to this later. But you see, when you cut this line over here, right, the both products will turn into carboxylic acid. As you can see here, the one on the left turn into carboxylic acid, the one on the right should also turn into carboxylic acid. So what's the second product? With 2 carbons, carbon 2 and 3, carbon 2 is the one that becomes a carboxylic acid. It's just how it works. Okay? So in other words, guys, do I do anything to carbon 3? No. Essentially, if you follow your numbering consistently, only carbon 1 and 2 will turn into carboxylic acid. Okay? It just oxidizes. It oxidizes into carboxylic acid. Only 1 and 2 okay, will turn into carboxylic acid.
We didn't know how the CH2 never.
Okay, so we'll get to that in a short bit. Okay, that's how we all start to ask. How come this one carbon doesn't turn into a carboxylic acid? Okay, actually, it does. You'll take a look at this first one. A 1 carbon carboxylic acid looks like this. You all agree? You all only see 1 carbon, correct? This is called metanoic acid. Because meta means 1. This is a very unstable compound. So it doesn't actually stay like this for long. It will instantly turn into carbon dioxide. Very unstable. So it can't stay as like this. Make sense? Okay, that's why it's carbon dioxide. But the rule still stays the same one. Okay? Now, of course, that isn't the end of it. Next one I want to try is I'm going to expand the thing one more. Okay, I'm going to draw 4 carbons. Same thing, I'm going to draw the products. Again, this is not balanced equation. All these are not balanced, but I don't care. Okay, I'm more concerned with you guys drawing the correct products. And if you want, okay, I'm going to draw even more examples. Try to use. Yeah, okay, just try these 2 more. There will still be more examples to go, right? Okay, this is just another 2 more. Okay, so let's check the answer. Number your carbons. You number them, number 1 must be the one directly bonded to benzene. 1, 2, 3, 4. This one got 1/5 carbon sticking up. Take a look at the products. Carbon 1 must be cut from the others. Carbon 1 must be cut from the others. Okay, so carbon 1 will turn into your white precipitate benzoic acid for both cases. The issue is always the next couple of carbons. So guys, take a look. Which carbon here becomes a carboxylic acid? 2. 2 is right literally at the cutting point, right? So you draw 2, 3, and 4. Only carbon 2, you just do a slight modification into carboxylic acid. Can you do that? Okay, so you number your stuff here. Again, over here, what's the next product? What should be our product here? Do we do anything to like which one do we modify? Okay, we only modify 2. So you go and draw 2, 3, 4, 5 the same, but only carbon 2, right, turns into a carboxylic acid. Something like that. Okay, so you'll see only those matter. Okay, this is 4, this is 5. Okay, the rest are untouched. You can see that. Okay. Now let's look at another example. Okay, 2 more examples. Now I'm going to start to branch out. Okay, number correctly. Okay, ready? Right. Okay, I'm gonna look at the first one because the second one is a bit special. Okay, so here, same thing, you must number this as 1 because it's directly bonded to benzene. Then there's 2 and 3. Okay, carbon 1 will become what first? Okay, benzoic acid, same as before. Okay, how about carbon 2 and 3? Now, first of all, right, you must make sure 1 is separated from everything else. You can see from the product, one is alone. So I cut 1 from 3. Understand it? 1 is still together with 2, so there's another cutting you need to do here also. You need to cut both 1 from 2 and from 3. Essentially, isolate 1. Everything else cut it away. Now notice carbon 2 is 1 carbon alone. Carbon 3 is also 1 carbon alone. If you have 1 carbon alone, what will happen? What will you become? Carbon dioxide. Can you see this? You have 1 carbon just there alone, you'll become carbon dioxide. But here, how many carbon dioxide do I get? 2. Because I have this guy alone, 1 carbon dioxide. This guy alone, another carbon dioxide. You can see that? So that's why this is 2 CO2. Okay. There are plenty more scenarios, okay, but I'm just going to go over this last one. Okay, how should we do this? Okay, so this one actually has no answer. Okay, there's no side chain oxidation here because there's another rule that I haven't really gone through yet. Okay, the rule is this: the carbon directly bonded to benzene must have at least 1 hydrogen. It's just a criteria for oxidation to happen. Okay, it must have at least one hydrogen, then all this can work in the first place. You look at this carbon here, does it have any H? Doesn't. Because it has 4 bonds that you can see. All these are alkyl groups, so it doesn't undergo side chain oxidation. You see that? Yeah, that's pretty much it. Alright, so I've gone through a few examples here, if you understand the technique. When you study that time, right, your job, you probably forget a few things, but your job is to how do you revise? You can find a pattern again, see what we just did, right? Okay, now at the bottom of page 30, there's something we need to discuss very briefly. Okay, it says that what happens if NaOH is used instead of H2SO4. Okay, come. Okay, just now you all see this, right? I use H2SO4 acidic medium, so I get a benzoic acid, a carboxylic acid, a purple color, decolorized, so on and so forth. But what happens if I change that to NaOH? First things first, can we predict the product? Do you think you're going to get the same product? What product are you going to get now? Why you say it's not the same product? Because when there's a base, a carboxylic acid is acid, right? You have the base, what will happen? You will get a salt. So the salt here is what? Is it CO2? It should be CO2 minus. Sometimes there's an Na plus there because it's NaOH. Okay, but in other words, guys, remember your acid-base equilibrium. This is the acid and this is the one. Okay, the salt, what's the term called? The acid and its conjugate base, because the base is always the one with one less H plus. The acid is always the one with one additional H plus. You can see that. Okay, acid conjugate base pair. You add the salt, you add the base instead, you're gonna get the conjugate. Okay, can? Now guys, let's predict the observations. What will happen to your KMnO4? What will happen to KMnO4? Okay, good. Okay, so your oxidation was successful. So purple KMnO4 decolorizes. But what else also happens? Now, if you remember, right, KMnO4 in a basic condition, you will also get this brown shade. Okay, brown precipitate of MnO2. So that's an additional observation. Now you compare with the initial one, okay, are you going to get a white precipitate of benzoic acid? Okay, is it benzoic acid? It's not, right? This is called benzoate salt because it's a carboxylate salt. So it's a different compound, but is it going to be a white precipitate or not? Okay, let's discuss this. If it's a white precipitate, does it imply it's soluble or insoluble? Okay, good. Benzoic acid here must be insoluble in water. We learned solubility here. But benzoate salt, I can tell you guys, there will be no white precipitate. If there's no white precipitate, it implies that this guy is what? Soluble. Now, we're write both of these structures down and write insoluble and soluble. Our job here is to kind of briefly understand why. Remember, chem bonding, they ask us to explain solubility, right? Can you all see what's the dominant interaction with this and water versus this with water? How does it interact with a water molecule? What's the main interaction? Wait, you say what is it? You say ion dipole is formation. Yes, there's an ion here. So this one is soluble because it forms ion dipole interactions. And we know, guys, ion dipole interactions, are they strong or weak? Okay, very strong. It forms ion dipole interactions with water, which are super favorable. Okay, this is very favorable. That's why it is soluble. You don't see any white precipitate. But on the other hand, guys, why is this insoluble compared to ion dipole interactions? Do you have ion dipole here? What do you form instead? The interaction, is it going to be stronger or weaker than ion dipole? It's going to be weaker. So what is the interaction? Okay, there's OH. Water is OH also. Okay, so this one you form hydrogen bonding. Now guys, even though hydrogen bonding is quite strong, right? It's quite favorable, right? Apparently it's not enough. Because you have a big fat benzene ring there, right? That also requires you to overcome these interactions. Benzene ring is polar, non-polar. The benzene ring is non-polar, right? It has ideally attractions to overcome also. It's very difficult to dissolve a benzene ring. Okay, because we also talk about how benzene ring very insoluble, right? Okay, that's why hydrogen bonding, right, is not as favorable now. Okay, and since it's not as favorable as ion dipole, it is just not enough to dissolve benzoic acid. That's right. Oh, it's because when you put KMnO4 and NaOH, right, you will form that.
Oh,
Yeah, it's just a byproduct of a basic medium. Okay, so we have just looked at some chem bonding stuff. Okay, any issues? No, huh? Okay, page 31, right? Both of those structures we drew already. Okay, so let's pick it up. Yeah, it's the same thing. Okay, let's skip this. We finished already. Okay. Okay, finally on our last page, page 32. Okay, distinguishing test. Okay, we finish this. Okay, later we can do something further. Okay. Yeah, okay, it's just. Okay, guys, come. Push through, push through. Okay, question 2. Okay, page 32. Can we look at the first one? Okay, remember, we are trying to distinguish between benzene and methyl benzene. Now, we need to come up with an answer here. What should we do? Okay, remember how to express your answer. Reagents and conditions you have to give me. Then you tell me benzene versus methyl benzene. The observations. What reaction should we use to distinguish both of these compounds? What is a reaction that only one of them can undergo, but the other cannot? Electrophilic sum. No, but both of them have benzene ring, so wouldn't they both undergo? Okay, so is free radical sum a possible answer? Again, possible, right? But okay, remember we mentioned before, FRS is quite a shit reaction in general. So let's not use FRS first. There's actually a better answer here. Okay, alkylation, halogenation, all of that fall under what's the umbrella term? We can't use halogenation, nitration as a term. It's all under electrosub. But remember, guys, both of them have benzene. Both of them can undergo electrosub. You cannot use that to distinguish. Any reaction that's only exclusive to one compound. Exactly, side chain oxidation. This guy has a side chain. That guy, no side chain, so use side chain oxidation. And I know the side chain that can also undergo FRS, but FRS is bad. Try to avoid that. Okay, so yeah, the answer here is just side chain oxidation, KMnO4, H2SO4, and heat. Okay, now go ahead and make a note to yourself. I know your school has taught you guys a little bit of heat under reflux. But if you write here heat under reflux, it is wrong. So go right there. Do not write heat under reflux. Okay, what does heat under reflux actually mean? Okay, heat under reflux looks something like this. It's a big ass setup here, right, with a condenser, right, so that it drips into another container. This right here is called a reflux condenser. Basically, to put it very simply, you just need to heat this thing for very long. Okay, you're gonna heat this thing for damn long, right? And then you need a full ass setup. But guys, why you cannot write heat under reflux for this kind of question? It's because they say here simple chemical test. And guys, when you conduct a simple chemical test, you know what? Yeah, okay, you conduct everything in the lab, but in a test tube to be specific. Basically, you must have test tube reactions. Okay, your reactions here must be test tube only. So guys, you can't use a freaking like reflux condenser. That one too big already. Okay, test tube reactions. So you can just keep the answer further. Okay, so anyways, okay, benzene and methyl benzene, what's the difference in observations? What happened to the KMnO4 in benzene? Does it decolorize in benzene? No. Okay, so okay, we'll go right now. But then your methyl benzene, okay, you know what? The observations are literally there. Okay, so it's just this is your answer. Okay, so okay. Okay, don't write nothing there. Just say that purple KMnO4 does not decolorize or remains. Purple KMnO4 remains. No white precipitate form. So just opposite it. Okay.
So the don't write heat under reflux is because once got heat under reflux, it's not important.
Yes, okay. The question highlight the word simple chemical test. You can only do a test tube reaction. Reflux is not a simple reaction. Okay, so there's that. Okay, any issues? Yeah, if we're gonna take a look at the second question, okay, can I just write this down again? Okay, we need to express our answer like this, right? But now we're gonna distinguish between benzene and not benzene, cycloalkane. Okay, what's one reaction that only one of them can undergo? That's exclusive to only one of them. Benzene can undergo one reaction. Just a default boring ass benzene. What can we undergo? What the full name? Electro sub, yes, that's the only thing you can undergo, right? Forget about an alkane. Okay, you can only undergo FRS, right? Okay, but which one should we do? Which one should we perform here? If you're given a choice. Yeah, okay, do electro sub because again, FRS is not a very good reaction. Okay, so we have no choice because each one of them can only undergo one reaction. But we choose electro sub over FRS. Okay, so for this guy, more specifically, there's so many different electro sub like options, right? We can either use NO2 plus, we can use halogen X plus, or we can add an alkyl group, right? Okay, so which one should we be using? Okay, why? That's correct. We have to use X halogen. Why? Because guys, this is a distinguishing test. What must you have in mind? The reaction that you choose, what's the basis for choosing a reaction? The reaction after undergoing already, you must be able to observe. Yeah, okay, there must be observations. NO2. There's no observations for NO2. There's no observations for alkyl groups. But if you refer back to the notes, there will be observations for halogens. Okay, more specifically, let's just use a bromine here. Okay, what's the other thing that you need to add? Bromine, what else? Benzene, electro sub need to add what else? Okay, AlBr3 is possible, but guys, remember what we mentioned, does it necessarily have to be Br just because we are using bromine? Okay, you can also use AlCl3, right? Because again, the whole purpose of this is to accept an electron pair from bromine. Bromine donate to aluminium, not the Cl, not the Br. Can see that? Okay, so in other words, AlBr3 catalyst, and finally, conditions are warm. Okay. Right. Why we use bromine? What's the observation you expect to see here? Okay, yeah, there's the color decolorized, right? Okay, so you just tell me, okay, Br2 is reddish brown. So for this guy, reddish brown Br2 decolorizes. For the next one, because you never add any UV light, is the bromine going to decolorize? No, it's not going to be successful. Okay, but on top of that, there's actually another observation. Okay, white fumes of HBr are formed. You can take note of this, this is also in the notes, okay, but we never really focus on that. Okay, now the reason for this is because when you take bromine and react it with a benzene, you're going to get a substitution, but at the same time, you're going to get HR. It's just a byproduct of the reaction. And take note, all these are actually white color fumes. That's why it's another observation you need to make. All okay? Yeah, that's pretty much it. Okay, so that's the whole of Arenes. Okay, we're gonna try a few questions before end off for today. Okay, next lesson we will do more questions now. Okay, but for now, let's just see what we can do. Okay, can you turn over to question 3? Yeah.
Yeah.
Okay.
Interesting, that's a great
You
lesson.
don't watch the lecture, right? You don't watch the video. Yeah, how's the learning? That's the excuse. Yeah, that was like 1 day. I'm going to at like 8 or even earlier than that, 6. Please go and watch. I'm going to look through again. Okay, before the tutorial. Okay, guys, look over at question 3. Okay, but yeah, school lecture you slow now. Yeah, okay. Let's figure out how don't burn out again. Okay, guys, come, let's go tutorial. We do question 3 and then we'll be done for today by then. Okay, come. Can we look at question 3A? Okay. This is a reaction synthesis question. A synthesis question is basically you're trying to make that thing. Okay, so can we look at the question now? They ask you to suggest a 3-stage synthesis. Now, usually as we go to higher levels, they won't tell you how many stages there will be. Okay, there are 3 stages, and benzene is the starting reagent. So, guys, what you need to do here is to turn benzene into that thing that's printed in the notes. Okay, in 3 stages only. So you have to exercise your creative thinking here. Okay, based on the information that we have learned just now, how do we slowly synthesize this data? Okay, perhaps for the first one, I'll guide you through a little bit. Okay, so question 3A, you should have to prepare your format first. Okay, benzene is the starting compound. This is the first stage. Okay, then of course you have something in the middle. Then you got the second stage, and then you also have the third stage. Okay, so they actually tell you guys how many. Go and draw in the final product. Okay, so you can see there I have CO2H and Cl. Right? You look at the start and you look at the end. Okay, I have 2 things to do. I have to put CO2H there somehow, and I have to put Cl also over there. Guys, number 1, is there a way for me to plug CO2H there directly? Have I learned the electrophilic sub of CO2H? Electrophile? No, there's no such thing. Okay, so that's why it's going to be multi-step. How do I put a CO2H there? Can we just study that first? How do we give birth to a CO2H? It came from side chain oxidation, right? So if side chain oxidation did happen, let's just write down all these reactions. For side chain oxidation to happen, you must first have a what? A methyl group, a side chain, right? You need to have a side chain. So guys, is there a way for me to place an alkyl side chain onto benzene? Can I somehow place an alkyl side chain on benzene? Possible, right? Electrosub, more specifically, electrosub of an alkyl group, alkylation. Remember, don't write alkylation as the reaction type. It is just electrosub. So guys, can see what's happening here. This must happen first, and then we can undergo side chain oxidation. So that's how the CO2H was formed in the first place. Okay, then of course Cl. Is there a way for me to place Cl onto benzene? Just one step directly. Can I do that? Yeah, okay, because electrosub also have the option of halogens, right? Okay, so that means guys, that's why there's 3 stages. Okay, I've written down 3 different things for 3 different steps. Okay, so can we just anyhow whack? Just whack whatever order you want. Does the order matter? That's the next question.
Yeah.
It will end up mattering. Because guys, what do we learn also? Okay, look at exactly what those positions are. How far apart are they? Like, let's just say this is the first position. This is the third. There's going to be a what directing effect? If there are 3 positions apart, there's bound to be a 3 directing effect, right? Okay. So you do not know what to put over there first. Never mind. Let's experiment. Let's put our chlorine there first. Okay, let's put chlorine here first. Now, guys, if you put chlorine here first, what's next? After you put chlorine, you look at the reactions we have just listed out. What should we put next? Okay, but to put an alkyl group, what is the directing effect of chlorine? So I must check on every step. What's the directing effect of chlorine? Okay, good. 2,4 directing. So guys, 2,4 directing means your alkyl group is going to appear on the 4th. Guys, is that on the right path? No, not at all. Are they 3 positions apart? You put here, are they 3 positions apart? No. So guys, you see, you cannot have a 2,4 directing effect. You must have a 3 directing substituent. You look at the final product there. What is a 3 directing substituent? A halogen, alkyl group. What's a 3 directing substituent here? Just check it out, nuclear again, don't guess. Okay, just see whatever that we have there. Okay, good. CO2H is 3 directing. So that means you're gonna need to have 3 directing first. Okay, go and play around with the order. I already tell you guys all the reactions are. Go and write the order from. Every step, go and check that out. Okay, don't worry about the reagents and conditions yet. That one we worry later. I want you all to get the sequence correct first. Okay. Okay. I'll go around checking your answer and then if you correct, then just go and find the reagent. So I realize reagents and conditions, wait, I'll go through it with them. Let me see your order first. Right. And try write CO2, if not COO.
Oh, okay.
Yeah. CO2 is going to be all by the side. Repeat the side. Okay, good. You all managed to get the order. Okay. You put CH3 first. Okay, just now you put Cl first, cannot, right? So you put CH3 first, no? Yeah, put CH3 first. But CH3, after that, can you put Cl? Still cannot, because CH3 is still 2,4 directing. So why not? You side chain oxidize him first to make him into 3 directing. Then the Cl will incoming go on to the 3rd position. So this is the correct sequence. Now, you can have the reaction types written down for each. But more importantly, I'm interested in the reagents and conditions. Come, take a look at this together. Guys, what's the reagent and condition for this? Okay, electron sub of an alkyl group. If you want to substitute a 1 carbon alkyl group, that means what was the electrophile? Remember, we went through this earlier, it means we need CH3+. But you can't get CH3+ because CH3+ is formed during the first step of the reaction, remember? Between the catalyst and whatnot. So what was the original compound? If CH3+ is the electrophile, is CH3, I'll just add a halogen at the back. And guys, then you add what? What else you add? You need a what to form the electrophile? Okay, the catalyst, right? AlCl3 catalyst. Can I use AlBr3? And also it doesn't matter. Right, okay, and finally, what's the condition? Default benzene. It's just one. Okay, we'll come to that. Yes. It's stronger conditions. Okay. Take a look. Guys, what's the second step here? Side chain oxidation, this one very simple. This one don't have any variation. So always H2SO4, KMNO4, heat, done. What I'm interested in is in the third step. Okay, take a look. Okay, third step, what am I doing? I'm E-subbing a halogen. Okay, so what halogen are we using? Okay, so add Cl2, what else? Al. Okay, catalyst. Okay, finally, guys, what's the condition? Okay, this is where it gets a bit tricky, because I want you all to look at CO2H. What effect does it have on the benzene current? Okay, go and write this down. Cannot remember again, doesn't matter. You have your data booklet. CO2H is what effect?
Huh?
Sorry?
3 directing.
No, that's the directing effect. I'm talking about the electron. Okay. It is p-activating, meaning it is electron withdrawing. Guys, does that make benzene more rich or less rich? Less rich. If it's less rich, means it's more reactive or less reactive? Less reactive. Okay, we draw this down. Guys, if it's less reactive, your conditions have to be stronger or milder. Stronger. So what do you use here? Yes. Okay, so we're going to highlight this part. You notice I haven't gone through this yet. Okay, that's why this question is important. In other words, there are three different conditions. You have room temperature, you have your warm, and then you have heat side. Okay, it's a spectrum. Milder conditions is room temperature. Stronger conditions is heat. The neutral one is just warm. Can see that? Okay, warm is just a normal benzene. No effect, no add-ons. Yeah. Okay, on the other hand, guys, CH3, what will happen? CH3 is a what effect? Alkyl groups are donating, which makes the benzene more rich, which makes the benzene more reactive. And then if you will have to react with this guy, which one do you choose? Okay, milder conditions, room temperature. Okay? That's reactive, you need to push it, right? So you really need to encourage it with a stronger condition. Okay, guys, I want you to give the second question a try, then we'll end off with the theory. Okay. Okay, remember what we did just now. Look at the final product first. Great. Plan out, pre-plan out what happened. Okay, what has happened to this molecule in order to get all these things. Don't care about the sequence yet, that one later you worry. You have to know first what to expect. Okay. Settle all the reactions first. The sequence they play with you afterwards. Yeah. Answer this is by calling. Okay, figure out the reactions first. Sequence we discussed separately. Can you tell me all the reactions that have happened? Okay, there is FRS. Good. Okay, you follow that FRS. Okay, that's E sub of your nitration. Okay, and yes, you must have alkyl group first. Then you can have this CO line. Okay. Okay, now tell me the order. Who first? Okay, so if you don't know, I'll just go and try and error. I'll go whack. Okay, but okay, you all tell me first. FRS first. No, not FRS. My bad. Alkylation first, followed by. Okay, FRS can also okay. And then ISA. Now, I know most of you guys will have from here ISA, then FRS last. I think that'll be a bit better. But take note, guys. This is still considered actually still considered an alkyl group. Okay, so you'll still be 2,4 directing still okay. Okay? Okay, so you want to do this, then NO2 last, then or you put NO2 first, and then finally FRS. It's not a bit more flexible, it's not okay. Okay, now let's just say we do this. So the first step is alkylation. Let's try the conditions. Okay, the condition here is right CH3 Cl AlCl3 catalyst. And what's the condition here? Warm. Okay, it's just a default benzene, it's not very simple. Okay, then afterwards, guys, what's the next step? Is nitration. Come, let's do it together. We need concentrated HNO3. What else? Concentrated H2SO4. Condition there. Remember, it's just room temperature, warm or heat. Here's room temperature. Okay, so guys, because CH3 is donating, donating makes the benzene more rich and hence more reactive. If you're more reactive, your conditions are milder or stronger. It already reacts by itself very a lot, right? So you don't need to push it very hard. Milder can already, so room temperature. Can? Yeah. Finally left. Okay, it's not FRS, it's not very simple. Okay, so FRS is just your PR2 and UV long. Yes. The order is it? Yeah. See, this one you just turn it around, then you get the one.
Wait, sorry, what is it there?
Okay, because this is donating, it makes the benzene richer. Richer benzene is more reactive. If it's very reactive, you don't need to put until so hot. Like a bit, okay, you can chill out with the guy a little bit more. Yes. Compared to this guy here, now the benzene is less reactive. He's now more lazy. You imagine a very lazy person, right? You need to really like scold the person, right? Make sure so you need to be stronger, harsher on the person, harsher conditions. This guy is more motivated, so you don't have to put him that hard. Yeah.
Wait, so can I do FRS?
Sure, can. If you want to do FRS first, go ahead. Then after that, still need to use your nitration room temperature still. It's the same electron donating effect. That one halogen doesn't change much, thankfully. Okay, can? That's it for today.